show. No, I do. I live in the back office. I do the computer work in there. I don't see the light of day. Anyway, we'll get this going. Problem 26.59 is can be very vexing if you don't get this point. It says you may assume theta is a small angle. That was written up there for a very important reason. If you can solve the problem without making that assumption with the math, you're pretty much going to have to either use guess or check to solve the problem, or a numeric method, unless you make that assumption. If you make that assumption, the problem's pretty straightforward. But we do have to go back to our physics 1. How many people is this familiar with? Has anyone not looked at this problem yet? Tonight. So what we have is we have some symmetry here. We have two masses. They're hanging by a string. Remember the little balls I had at the beginning. And they have some charge each. They each have the same mass. We know the length of the strings, and we're asked to determine the angle. How on earth would we go about solving a problem like this? So this is combining what we know now with what we knew last semester.
Break up each force into their components.
That's a good thing. We can break up each force into its components. You're getting a little ahead. Let's step back, and before we even do that, when we were assessing the problem, trying to model it, what will we need to do? We need to look at what kind of assumptions do we need to make. We will get there, that's you're right, but what do we do before that?
We need to be able to identify the forces, which means we need to make assumptions regarding how the system works.
Right, we need to make some assumptions and model it. I do like the idea of identifying forces. For example, the two masses, we'll treat them as what's particles. And we can identify what forces do we see on each of those charges, charged objects. There is symmetry, that's good. But what, can you tell me a force that's on either of them, or both of them?
Tension.
Tension. So there's a tension force on each of these. And the tension will always be in the direction of the string. Since there's symmetry, I'll just use 1T. If there wasn't symmetry, I'd have to say T1, T2. Are there any other forces? What's that?
Electric.
Electric. What direction is electric force on the charge on the right? The same charge, so the repulse of forces, so there'll be a force electric this way, there'll be a force electric that way. Are we done?
Gravity.
And we will not neglect gravity in this instance. All right, any other forces? Probably not. From here, where do we go? We're almost to where you were at.
We can sum the forces.
Before we sum the forces, I would always like to draw a free body diagram. So what is our object of interest? Or what are our objects of interest? I think I heard someone say it. The charges. The charges. Since there's symmetry, I could look at just one of them. Does that make sense? So we can go over here with tension, the y-axis, the x-axis, theta. What is the force of electric people here?
QE.
QE, yeah. And what's E equal to? We we not say K, Q, Q? Over 2T. So K times Q1 times Q2 all over the distance between them squared. Now, we can break the two forces into components and sum them. And what you'll find is that, see, if we break the tension into its components, what would the tension be equal to? See, what's the tension in the x direction, positive or negative?
Negative.
Negative T sine theta. And the y component? Positive or negative? Now, what does this small angle stuff tell us? This makes our life a lot easier. So for a very small angle, sine theta is equal to theta. Assuming theta is measured in radians. This becomes our life becomes a lot easier at that point in time. The rest of it then becomes summing the forces and doing a little bit of algebra. Is this a question?
How are we supposed to know that?
If you read the problem, it says you may assume that theta is a small angle. That's physics for saying sine theta equals theta, cosine theta equals 1. What would tan theta equal? Sine theta divided by cosine theta, which is theta divided by 1, which is theta. From here, this problem is pretty straightforward. There's two other problems on this homework that you should be able to do in your head, because there's just scaling. We're changing charges or we're changing distances. If we double the distance, what should happen to the force?
Quarters.
If we keep all things equal. If we have an electrostatic force, it should be 1/4. If we quadruple the distance, what should happen to the magnitude of the force?
1/16.
1/16. We have the distance. Force becomes 4 times bigger. If we double the charge, the force should
Double.
if we double the charge on one side. If we double both charges, then we should quadruple. You do that, you do this, the homework's pretty manageable. What? You guys are tired? Wake up. Monday morning.
It's Monday.
It is Monday, I know. I hope this means at least you had a lot of fun this weekend.
I feel ya. I'm always sad it's over, even if I didn't do anything.
See if we can get things going a little bit.
This should be a good quiz for Monday morning. Any questions before we start? Last chance before we go. Now, the answers won't be a question I'll answer yet. I will, but after you play. Any other questions? All right, that's good. Three, two, one, good. It looks like we're all there. Yes, all right. You're not gonna, must be here. Might be tired, but not that tired. All right. We have a quick in-house fix going on. Pressure's on. Got it?
Yeah.
All right. NASCAR pit stuff, I like it. All right. The negative charged object, what will it do to the electrons? It's going to repel them, right? So you certainly don't want to track them. So the D is not an attractive answer. The rod, the ball's neutral, right? So it's not an opposite charge issue. Definitely should be C for it, please. Nice. Remember, eta is the surface charge density. There's some plastic, there's a charge uniformly spread across it. We're going to break that surface into a bigger piece and a smaller piece of the charge density for those pieces. Oh, you guys are not ready. Excellent. Oh, almost.
So close.
All right.
That one person.
Two out of those two.
First I thought you said
Now we're
baby
awake.
sirens, and I was like, what? Baby sirens? Are we talking like a mythical creature, or like baby versions of fire trucks?
Alright, let's come back together. So on Friday, we looked at things in a rather complex way. We took, and instead of looking at a discrete number of source charges, we looked at an infinite number of source charges, and we talked about the fact that we can integrate to find the field at a certain point in time. But I did insinuate there's an easier way to determine the field without going and doing all that integration. And what I want to do today is start to develop that sense of what that method is. It's going to introduce this new concept called flux. And then on Wednesday, we're going to use flux to determine what the field is around objects like a spherical charge or a long line charge that will avoid all the nasty calculus. If you go on and take a second class in electromagnetism, you'll do lots of that integration. I'm not going to emphasize it now. What I do want to emphasize is this way of thinking about it that we're going to develop here, and this idea of flux, and then this thing called Gauss's method. So, and the other thing I want to talk about today is what happens when we have particles not in a static situation like this, where what are some of the forces on this charge? Zero, actually it's chopped out because it's static. But what if we have an electron shooting through a field? What will its motion look like? And it used to be really important to us because our TVs used to be electron beams that got deflected, but our TVs also weighed like 100 pounds and had big tubes in it. Same with these things, they didn't come flat a long time ago. So, this will be an equation sheet. Become familiar with it, be able to use these. We will derive these from Gauss's law. If you really want to have some fun, be able to derive these using calculus. If you're going to go on in physics or anything, that'd be great. Come by the office and we can work on doing that. But what I really want to emphasize is using Gauss's law. So the first question is, if I have a large plate, let's go back there, how does that compare to the gravitational surface of the Earth? So if we look at the electric field, what do we notice about the electric field lines going up from that plate? They all, imagine this big surface of charge, it's infinitely large. They all go up. Would it make sense for the electric field above this surface to be pointing to the left or to the right? Why would it point this way rather than this way? And then, how would the field strength at this point here compared to this point over here? It would be equal. As we move away from the surface, is there any guess at what the field does?
It's smaller.
It stays the same. So if we look at the electric field above this large, infinitely large surface, the field points up, and it's uniform. It doesn't get bigger, it doesn't get smaller. How does it compare to the gravitational field near the surface of the Earth? The gravitational field points down. Right? How does the field here compared to the field over here? It's the same. So I have this uniform field. If I drop a mass, or I throw a mass, which direction is the force on that mass? Straight down. So if I throw it in this direction, let's assume that up is the y direction, to your right is in the positive x direction. As I throw that mass and it's flying through the air, how does it accelerate in the x direction? No acceleration, right? Now, is that true? No, there's really a little bit of air drag, right? So there's some friction. So there actually will be some acceleration in the opposite direction. But if we ignore friction or drag, there will be no acceleration. What about in the vertical direction? Will there be any acceleration? Yes. What do we call that type of motion? It will be a parabolic motion, or the other word is constant acceleration in one direction, uniform motion in the other direction. We call that projectile motion. We will see a very similar type of motion if we have a charged object moving through. Imagine this is a charged object. It's now moving through an electric field that's uniform because we're near a large plate. If the electric field is up and this is negatively charged, what direction is the force on this negatively charged object? Electric field's up, this is negatively charged. Is the force down or up? Down, good. You imagine that the math on this is just the same as the math. Now the difference is the electric field can be going this direction and it's now a positive charge. Which direction's the force? To your left. In which case, if I gave it an initial motion in this direction, it'll accelerate to the left and it'll have uniform motion up and down. Neglecting gravity. So we'll treat, in both cases, we'll treat the fields as uniform. The force on a mass near the surface of the Earth is treated as constant. The force on a charged particle in a uniform field is treated as constant. The math's a lot easier this way. When you get to more advanced dynamics, you'll look at varying fields and what the motion looks like. But we don't want to deal with that yet. We will set up the problems just like this. We'll identify the forces, we'll identify the object of interest, so we'll model the problem, then we'll draw a free body diagram. We'll get to summing the force, breaking the forces into components. We'll sum the forces in the x direction, we'll sum the forces in the y direction, and the sum of those forces will be equal to the mass times acceleration. If it's a statics problem, then that mass times acceleration. The motion will be parabolic or will have trajectory motion, or projectile motion. All right. Now, reading these is confusing sometimes. If we have an infinite plane, we can look at it like that or up there. This is some kind of three-dimensional drawing where we're imagining the plane is like this, and we have the field moving up away from the field this way, and down this way. If you look at it from the side, it looks like this. How can you tell that's not a wire? You really can't, okay? So you do have to be real careful when you're reading the problem. Is this an edge view of a plane, or is that the edge view of a wire? And unless you read the context, you won't be able to tell. So just be cautious for that. So here's two thoughts. What if we have two large charged plates and we bring them next to each other? And remember in your kit you have that green thing? It's round. For lab. Those are capacitors. Inside there's several long sheets of metal separated by an insulator. And so there are two large plates. It doesn't look like a large plate, does it? It looks more like a tuna fish can. The reason is they're very, very long sheets of conductor. They're very thin, and they're rolled up. And then stuck in that can. Otherwise, the capacitor, the larger the plates, the more capacitance. Otherwise, that capacitor would be really very big. But to conserve space, they roll up. But imagine now that we have two plates next to each other. What would the fields look like? So I'm going to divide. This is an edge view of a plane. field. It's uniform on both sides, right? And the electric field moves away from those plates. What about the negatively charged plate? No surprises there, is there? What if we take two plates, one that's positively charged, it's got a certain positive charge density, and this plate over here is negatively charged, and we bring them close to each other? Oh, let's do one other thing. The field here these two plates have been brought next to each other. One has a positive charge density, the other one has a negative charge density. They're in all other ways identical, except that one has a positive charge, the other one has a negative charge. What is the field contribution from the positive plate right here? And from the negative plate? How do the magnitudes of those two fields change, compare? So, what's the net charge here? The net field, excuse me. There's zero field. What about here? 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 Zero. There's no field out there. What about over here? From the positive plate, which direction is the field? Outward. And from the negative plate? So when they add together, what's the net field? Zero. What about here? Which direction is the field from the positive plate? To the right. And which direction is the field from the negative plate? Right. So does the field cancel between the plates? No, it adds together. We'll have eta over 2 epsilon, so plus eta over 2 epsilon equals
Because the positive plate is just slightly farther away from the negative plate from the right side, should there be just a tiny negative field on that side and a tiny positive field on the left side? I mean, almost negligible enough, but should they be not equal to zero necessarily?
well, how does the field, let's ignore the two plates. If we go back to just the positive plate, how does the field at this point compare to the field at that point?
Should be stronger, right?
For an infinite plane, it does not change. What's the difference in gravity here and here. If we assume that the planet's spherical, then it's slightly different. But if you imagine if the mass of the Earth were infinitely broad, if it truly was a plane, in that case there's no difference. In the same way, if the if the plate was infinitely large, there would be no difference between the two fields. Now, are there any infinitely large plates? No. Will there be some slight variations? Yes, just like there really are some slight variations in gravity between here and here. It's just not discernible. So, these are models. Models give us insight into the truth, but they're not perfect. There's no gauges. Does that seem so bad? Now, what I want you to think about, we won't go over in class, what if this had a different charge density than this? Would we expect the field out here to be zero in that instance?
No.
What about if these were both same charge? They're both positive.
To
How
repel
would
each
that
other.
change things? It'd be a cancel in one place and there. Would it be different? Any questions how we reason through this? Yes?
How come it's from the positive to the negative, but not from like the negative to the positive side?
All right. Remember that we determine the field, we'll take a small test charge, a small positive test charge. We'll put that small positive test charge and we'll think about what will the force be. We have a positively charged object with a small positive charge near a large positive plate. Which direction will the force be on that positive charge? It'll be away, right? What if we put the charge near a negative plate? Which direction would the force be? So, if we imagine that the field is equal to the test charge divided by the force, and we measure the direction.
So it's based off a positive test charge? Is that-
Right.
Okay.
So we can think of fields as being, we put a positive test charge, what direction will the force be? We divide that. That should be the other way around. Now that's how we're going to, what units does that give the field then? It's a great moment. Newtons per Coulomb, right? We also get the same if we plug in A to the charge density divided by epsilon naught, we'll get newtons per Coulomb. All right. Now, if we put now let's imagine that we shoot an electron up through here. What will the force be on that electron as it goes through the electric field? F will be equal to Q times E. E is to the right, but since it's an electron, it'll be a negative charge or in the negative direction. The negative, does that make sense? Would an electron have a force to the left? Would it be attracted to the positive plate and repelled by the negative? So the electron's path would be accelerated to the left. What about if the electron was shot through space over here to the left of the capacitor?
Just those straight.
Which direction is the electric force on it? No electric force. Why is there no electric force? There's no electric field. Beautiful. All right. Now, a real capacitor, the plates are not infinitely long, so there's what they call fringing out here. The field, if there actually is an end to the plates, it will fringe out. We've covered all those questions. What's the force on an electron here compared to the force on an electron over here? Does the field strength change? No. So does the force change? What about here? Force change there, in the right dead center? Different from here? What about on the side of the capacitor? All right. Cover those. Okay, now I want you to think about these. If we have time, we'll come back. So what if 81, the charge density, the one plate does not equal the other? What if the charge densities were both positive? How would that affect? So the electric force, positive charged particle is placed between the in a uniform field. How does the location change the electrostatic force? At points A through E, the force is the, what if it's a positive charge? Same story, right? Any questions? Now a dipole, if it's an electric field, what happens? You have a uniform field here. What direction is the force on the negative side? Oops, thank you. The force on the negative side, to the left, on the positive side. To the extent those two charges are the same, what's the net force on that object? Zero. So it's polarized, whatever we have here, because maybe it's an electron cloud. The electrons have been cloud has been attracted to the positive side, repelled from the negative side, but the net charge is the same. The net force is zero. So it's polarized it, but the net force is zero. What if, however, we have some molecule that naturally has some polarity, and for some reason it's aligned this way? Now, what direction is the force on the negative side? And the positive side? The net force is still zero, but that force is above the center of the object. This force is below the center. Now we can't treat it as a particle. If we have a force some distance from a point, what do we call that? The torque. So there is a torque, a counterclockwise torque from that force. What about the direction of the torque from the positive? It's also counterclockwise. There's a torque that wants to align that molecule with the field. So that's what we're getting at here. Remember we defined the dipole moment as the distance times the charge. We call that P. The torque on that dipole will be the dipole moment P cross product the electric field. So in that case, dipole moment cross give us a torque. Remember the torque, the direction of the torque is the axis of the rotation. Everyone comfortable? Any questions? Near a point charge, the same thing will happen. Now, there's a little bit of different strength around the dipole moment because the field does change around the negative and positive, but there's still a sense that the dipole wants to align with that field. So if we have a neutral object, it's near a charged object. If there's any dipoles inside that neutral object, so there's atoms that become dipoles, they will align with the field, and you can imagine that now, let's see, the dipole in this instance, what was the net force? 0. What about the net force on this dipole? Is the electric field here the same as the electric field there? No. So the force of attraction on the negative side is a little bit greater than the force of repulsion on the positive charge. There will be a net attractive force, and so the dipole will be attracted to the point charge. So what would that imply about a neutral object that polarizes inside the capacitor? Would there be any force on it? No. If you have a neutral object that can be polarized near a point charge, will there be a force of attraction? Right? This is how the old TVs used to work. Outside of the plates, the electric field is essentially 0. We can shoot electrons through. If we vary the charge on the plates, we can vary the deflection of the electron. So we have uniform motion here. We have uniform in both directions. Between the plates, we have uniform direction in the uniform motion in the horizontal. We have constant acceleration in the vertical. Once the electron leaves the plates, it goes to completely uniform motion. Changing topics. I cut a block out here. I didn't want you to know it was in the middle. Oh, by the way, I've changed it. We're introducing something new here also. Are those electric field vectors? No. I've replaced the field vectors with field lines. It's hard to visualize what a field looks like. In trying to draw field vectors gets very time consuming. Plus they start to cross and there's all sorts of confusion. What we can do is we can replace those field vectors with this concept of field lines. And what we'll do is we'll say, at every point in space, we'll say which direction is the field pointing. And then we move a little bit in that direction and say, now which direction is it pointing? And now which direction is pointing? And if you can imagine, there's a path. So imagine we want to measure the elevation. We always want to walk in the direction of the steepest downhill. That's somewhat like a field line. So it's always telling you which way the field is pointing, and we're walking along those paths. Well, where those field lines come together, what does that imply about the field strength? It's become stronger. Here, where the field lines are the same direction, they're not becoming more dense or less dense, the field is uniform. Where the field lines are spreading out, that implies that the field is getting weaker. Here's my other. So imagine the field's always pointing out from this point source, right? So as we get close, this is a positive charge, the field go out in space. As we get farther and farther apart, as those field lines separate, the field gets weaker. As we get closer, the field lines become more and more dense. So what's missing in that picture? Charge. Which kind of charge? Negative charge. Any guesses what's over here? Positive charge. If field line started a positive charge, it ended a negative charge. The field's weaker out here, the lines are farther apart. They're stronger near the negative charge. Anyone surprised? It's a good thing. We're starting to get a sense. Now, if that's a point charge, we've represented the field in 2 dimensions, but this is a 3-dimensional. We have another point charge here. The field lines are moving from the positive to the negative in all 3 dimensions. So if the field lines are emanating from the point, what does that imply about the point? The field lines are all spreading out from a point. There's a positive charge. If the field lines are all converging on a point, what does that imply? Negative. What we're going to do is imagine putting a box in space, or a sphere in space. And we're going to look at the field lines going into or out of that sphere or box, or whatever shape we're going to encompass a volume of space with. If there's more field lines going into that box than coming out, there could be some coming out, but there's more going in. What does that imply about the net charge inside that box? Negative. What about if the net field lines going in is net number of field lines is going out rather than in? Implies the net charge is positive. We're going to introduce this idea of flux. Flux would be somewhat like counting the number of field lines going through a surface. So in the case of a uniform electric field going from left to right, imagine I'm going to make a surface here. Are there many field lines going through this surface right now? Imagine the fields going from left to right. So there's this uniform field going from left to right. And now I'm going to create this surface and hold it like this. Are there many field lines going through it? Imagine, another way to think about it is imagine there's a fan that's blowing wind this direction, from left to right. Is there air going through that circle? Yes. The same way, if the field lines are going from left to right, there are field lines going through it. Now, the air is still moving from left to right, or the electric field is moving from left to right, and I move my surface like this. So this is a round surface. Let's imagine that the surface is inside my arms. I'm trying to be a loop. Now, is there much wind going through my arms? Why not? The area of the surface hasn't changed, has it?
It's perpendicular where the wind is.
Maybe it's, I'll use a paper. Imagine we have field lines coming through. Are the field lines piercing the paper now? If I go like this, are they piercing the paper? They're going to go above and below, right? So the direction of that surface matters. I'm trying to going to be important when we calculate the amount of field going through a surface to figure out the direction of the field and the orientation of the surface. So we're deciding whether field lines are converging or on a point, or whether they're diverging from a point or volume of space. We need to know the orientation of the surface relative to the orientation of the field. Well, this whole concept that electric fields leave a net positive charge or go into a net negative charge has a law. So that's what I was trying to talk about with the surface. And what we're going to do, let me go where I'm going. Where we're going is we're going to say, if we add up all the field lines going out of the surface, that'll be equal to the net charge inside the surface divided by this epsilon naught. And that'll tell us something about the number of field lines that come out. But we need to understand what this net number of field lines coming out is. And what we're going to do is we're going to call that net number of field lines coming out the flux. And if we know the flux from an enclosed surface, then we'll know what the net charge is. But calculating this flux is a bit tricky. So imagine we do have a ring and we have an electric field that's going through that surface, that's just a round surface. If the electric field isn't coming directly perpendicular, there's some difference in angle between the tangent to the surface and the electric field, then the amount of flux will be less than if those two were completely oriented. So if the field and the tangent to the surface are oriented, we just look at the area of the surface times the electric field, and that tells us the flux. If they're perpendicular, if the tangent to the field and the electric field are perpendicular, then there's no flux through the surface. If they're at some angle, it works out that the relationship is the dot product, or the electric field times the area times the cosine. What it is, if you look at it, the area vector that's perpendicular to the surface, the electric field, if you look at the component of the electric field that's perpendicular, that component is going through this times the area gives you the flux. That's where the dot product. We will go over this idea of flux, field line, Gauss's law.